Okay, so this is going to be a read through of Chapter 6, Section 2 on electric current. It says, before you read, have you noticed that one end of a battery is marked with a plus sign and the other end with a minus sign? What happens if you put the batteries in a flashlight in the wrong direction? Most of you probably know this, but it doesn't work. So that's what we should write on this line right here. Okay, similar to last time, we're going to highlight as we go some of the main things, and I'll point those out to you. There's quite a bit more in here. So here we go. Current and voltage difference. You have read about the ways electric charges move. One example is the spark that can jump between your hand and a metal doorknob. And we'll highlight this. Electric current is the net movement of electric charges in one direction. To understand the net movement, consider the movement of electrons in all materials. In all materials, electrons move in every direction. Since the electrons are not moving in the same direction, there is no electric current. When electric current flows in a wire, the electrons still move in all directions, but they also drift in the direction that the current flows. The drifting of the electrons is a net movement in one direction. And we should highlight this whole part here that I just read. When electric current flows in a wire, the electrons still move in all directions, but they also drift in the direction that the current flows. The drifting of the electrons is a net movement in one direction. And then we're going to highlight this whole paragraph here. Electric current is measured in units called amperes. Amperes are also called amps. The symbol for amperes is a capital A. Amperes measure the electrons that flow past one point. 1 ampere is equal to 6,250 million billion electrons moving past a point every second. Okay, now we're going to answer question 1 on the left. How many electrons move past a point every second to equal 1 ampere of electric current? It just told us in the reading, and we should have this whole paragraph here highlighted, but so 6,250 million billion electrons move past that point every second. That equals 1 ampere. What is voltage difference? Even though the electrons are moving in all directions, an electric force acts on the charges to make them flow in one direction. We're going to highlight this sentence. Voltage is the electric force that makes charges move. Voltage is also like the force that acts on water in a pipe. Water flows from higher pressure to lower pressure. In the same way, and we'll highlight this, electric charge flows from higher voltage to lower voltage. We're going to keep highlighting. A voltage difference is related to the force that makes electric charges flow. Voltage difference is measured in units called volts, and the symbol for volts is capital V. What is an electric circuit? Look at the figure. It shows an electric current doing work by lighting a light bulb. Electric current must have a closed loop-like path to follow. If there is no closed path to follow, the current stops. We'll highlight this sentence. An electric current is a closed path that electric current follows. If the circuit in the figure is broken by taking away one part, such as the battery or light bulb, current will not flow. It will also not flow if a wire is broken or cut, and the light bulb will not light. Now we'll answer question 2. Look at the figure of a circuit. Which direction do electrons flow in the circuit? Away from the negative terminal or away from the positive terminal? They flow away from the negative terminal. And you can remember this because they're going to be attracted to the positive terminal since electrons are negatively charged. Batteries. A circuit needs a voltage difference to keep electric current flowing in it. A battery can provide the voltage difference that keeps electric current flowing. Look at the figure of the circuit again. The positive end and the negative end of a battery are called the terminals. When a closed path connects the terminals, the current will flow. And in this, we want to just highlight the second sentence. A battery can provide the voltage difference that keeps electric current flowing. So on to how do dry cell batteries work? The batteries used in a flashlight are called dry cell batteries. Look at the figure below of a dry cell battery. The battery has two electrodes. One electrode is a carbon rod, the other is a zinc container. Around the electrodes is a moist paste. The paste is called an electrolyte. The electrolyte contains chemicals that are conductors. The electrolyte lets charges move from one electrode to the other electrode. This kind of battery is called a dry cell because the electrolyte is a paste, not a liquid. Now we're going to, in this we wanted to highlight the electrolyte contains chemicals that are conductors, and the electrolyte lets charges move from one electrode to the other electrode. So highlight those two sentences. And then we're going to answer, what is used as an electrolyte in a dry cell battery? Right, and this is just a moist paste, or you can just say a paste. All right, on to our next page, making electricity. And we're going to highlight a lot of this one. So we're starting off, we're going to highlight when the two terminals of a dry cell battery are connected in a circuit, there is a reaction between the zinc and the chemicals in the electrolyte. Okay, we highlighted that whole sentence. We can stop highlighting for the moment. Electrons move between some of the compounds in this chemical reaction. We'll highlight the carbon rod becomes positive. Okay. The positive terminal is marked with a plus sign. We're also going to highlight right here, electrons build up on the zinc, making it a negative terminal. The negative terminal is marked with a minus sign. The voltage difference between the terminals causes current to flow through a closed circuit. Now we're going to answer number 4. When the chemical reaction, describe when the chemical reaction occurs in a dry cell battery. Okay, and it's asking for when. Okay, and it said right at the top here, we highlighted, right, the reaction will occur when terminals are connected in a circuit. Then a reaction will occur between the zinc and the chemicals within the electrolyte. Okay, so if they're not connected in a circuit, then you're not going to have those chemical reactions occurring, which is why your batteries aren't really going to drain very much if they're not, being used, if that circuit's not closed. When you turn a device off, the circuit gets opened, and since it's open, it isn't draining the battery. Right? The circuit's only running and using batteries when it's closed. Okay, how do wet cell batteries work? Another kind of battery is the wet cell battery shown below. A wet cell has two connected plates made of different metals. The metals are in a conducting solution. Chemical reactions, and this is what we want to highlight, these next two sentences. Chemical reactions transfer electrons from the lead plates to the lead dioxide plates. This battery is called a wet cell because the conductor is a liquid. A wet cell battery contains several wet cells that are connected. Together, the cells give a larger voltage difference than each of the cells alone. We're going to answer number 5. What two things are shown in both the figure of the dry cell battery, which was before, right here, and the wet cell battery? You can take a minute. You can pause this video if you want and look at both of those and compare. And it is the positive and negative terminals, right? Both a dry cell and a wet cell battery have positive and negative terminals. What is a lead acid battery? Lead acid batteries are wet cell batteries, and they are usually used in cars. And we're going to highlight those two sentences. A lead acid battery has 6 separate wet cells that are connected. The cells are made of lead and lead dioxide plates. The plates are in a sulfuric acid solution. A chemical reaction gives a voltage difference of about 2 volts in each cell. And there are 6 cells, so the total voltage is 12 volts. How are electric outlets different from batteries? Electric outlets, such as wall sockets, also give a voltage difference, but this voltage difference is usually much higher than the voltage difference a battery gives us. Most wall sockets give a voltage difference of 120 volts, and some outlets have a voltage difference of 240 volts that is needed for large appliances such as electric ovens and clothes dryers. So that's way, way more volts, and volts equals danger. Resistance. Oh, I'm sorry. In that paragraph there, we should have highlighted the first two sentences. Okay, electric outlets such as wall sockets give voltage difference, and the difference is usually much higher than batteries. All right, resistance. On the next page, flashlights use dry cell batteries to make the current that lights up the light bulb. What makes a light bulb glow? Part of the circuit is a thin wire in the bulb. The wire is called a filament, and you guys have probably seen that. The electrons in the current flow through a filament. As they move, they bump into the metal atoms in the filament. And then we're going to highlight these next two sentences. The electrons bump into the metal atoms, turning some of their electrical energy into thermal energy. The metal filament gets hot enough to glow. The radiant energy lights up the room. Okay. And let's do, how do materials resist current? And then we'll answer question 6. Electric current loses energy when it moves through material because of resistance. Resistance, we'll highlight this in these next few sentences. Resistance is the tendency for a material to oppose or go against the flow of electrons. Resistance turns electrical energy into thermal energy and light. Almost all materials have electrical resistance. Materials that are electrical conductor, we're going to highlight this as well, the rest of this little part. Materials that are electrical conductors have less resistance than materials that are electrical insulators. Resistance is measured in units called ohms, and then that's the symbol for ohms. It's like the Lululemon symbol. Okay, which it actually is. They use ohms as their little logo on their pants because of like their yoga pants. So ohms, like it's a kind of a pun. All right, so now let's answer question 6. List the 3 types of energy needed to make a light bulb in a flashlight glow. So first you're going to need electrical energy, right? That has electrons moving through the circuit. Next, we're going to need thermal energy. First, it's going to be turned into heat within that filament in the bulb. And then we're going to need that to get so hot that it glows and becomes radiant or light energy. So those are the 3 types: electric, thermal, and radiant, aka light. All right, what can affect resistance? The temperature, length, and thickness of a material can affect the electrical resistance of the material. We're going to highlight, usually the hotter something is, the more resistance it has. Okay. The resistance of an object also depends on its length and thickness. We're going to highlight, the longer the circuit is, the more resistance it has. Resistance also increases, well, keep highlighting, so resistance also increases as the wire gets thinner. All right, a light bulb filament is a thin piece of tungsten wire made into a short coil. The uncoiled wire is about 2 meters long and very thin. Tungsten is a good conductor, but since the wire is so long and thin, it has resistance. The resistance makes the filament glow. We'll highlight this last sentence here. The more resistance a filament has, the brighter it glows. And then we're going to answer question 7. How does the resistance of a filament affect its glow? Well, we just basically answered this in the reading, right? If we increase the resistance, it will glow brighter. So, and the opposite is also true. If that filament had less resistance, it would be dimmer. The current in a simple circuit. A simple circuit has 3 main parts, and we'll highlight. First, it has a source of voltage difference, such as a battery. We'll keep highlighting. Second, it has a device that has resistance, like a light bulb. Still highlighting. Third, it has conductors such as wires. The conductors connect the resistance device to the battery terminals. When the wires are connected to the battery terminals, the path is closed and current flows. Two electric circuits are shown in the figures on the next page. Each circuit is a battery connected to a light bulb by wires and a rod. The circuit on the right is shorter because the wires are closer together on the rod, and that circuit therefore has less resistance. So here's the pictures. Okay, we have this. They're the same picture exactly, except on the one on the left, as it has this rod. It's taking up more of it. So that's a metal rod that's basically being used as a wire to pass current through. And there's, a greater length. So this is overall a bigger loop. And this is a smaller loop, shorter path, but they're otherwise identical. All right. The voltage difference, current, and resistance in a circuit are related. If the voltage difference stays the same as the resistance decreases, I lost my spot for a second. The current in the circuit increases. If the wire is short, the light bulb will be brighter. And I actually want to highlight that because I feel like it's something we should remember. If the wire is short, the light bulb will be brighter. If the resistance doesn't change, increasing the voltage difference increases the current. If you use a larger battery, the light bulb will be brighter. Now we can answer question 8. In which circuit will the light be brighter? The one on the left or the one on the right? Okay, this would be the one on the right is going to be brighter because it has less resistance. So it's like it will have more, we already said that. If the wire is short, the light bulb will be brighter. It's what we just highlighted in this little part here. Okay. What is Ohm's law? There is a relationship between voltage difference, current, and resistance in a circuit. Ohm's law states that the current in a circuit equals the voltage difference divided by the resistance. I stands for electric current, so Ohm's law can be written as current in amperes is equal to voltage difference in volts divided by resistance in ohms, or I is equal to V over R. We're going to use this lots and we'll get tons of practice. So Ohm's law can also be used to measure resistance. We change the equation around so that resistance is alone on one side, and we do that by multiplying both sides of the equation by R, and then divide both sides by I, and then the new equation becomes R equals, or resistance is equal to volts divided by current, voltage divided by current. And then it gives us an example of plugging them in, but actually we're not going to be doing that today. We'll have plenty of time to practice that later. So you do not have to do number 9. And then we're going to skip to this is our last page. I'm not a fan of these ones, so we have to do number 1. And we're not going to do number 3, so we're just doing number 2 on the last page. Complete the table below to describe a simple circuit. The first column lists parts of a circuit. The second column, you should give an example of each part. And under the heading function, write a short description of what job each part does in the circuit. So voltage difference, a good example is a battery. And function, it's going to keep current flowing by creating a voltage difference. Current will flow from high voltage to low voltage. Source of resistance, something like a light bulb, a device that resists. So I wrote light bulb as my example. And then for function, it's a device that resists the flow and converts electrical energy into thermal and or radiant energy. And lastly, conductors, I picked wires and their function, connect the resistance device to the terminals for the battery or the sockets, like wall socket. Okay. And that's it. So hope that goes well for you guys, and I will see you on Thursday.